At this point, we know how to solve linear systems of equations by transforming them into augmented matrices, applying elementary row operations, identifying the pivots, and then using those to make a description for the solution space of that linear system. Our job now is to take a big step back from that process and figure out what is it that we're really doing when we're solving a linear system of equations. Is it really about trying to solve for a collection of real valued variable quantities and discovering what x is, y is, and what z is all separately? Or is it about something bigger? It turns out, and this is the vocabulary we want to begin to build right now, that linear systems of equations, and in fact linear algebra generally, is not about collections of real valued variable quantities. It's really about objects that we call vectors. Vectors are going to be the main object on the stage of linear algebra. It's also about matrices. A matrix is something that gives vectors directions on that stage. It gives them their lines, it gives them their blocking, it gives them their cues, it gives vectors something to do. So we want to move from our chapter 1 viewpoint of thinking about linear systems of equations as defining the values of several variables kind of in collection with one another. We want to think of them instead as defining values for what we call a vector valued quantity. So we want to be able to bundle those quantities together into a single entity that we call a vector and think about solving a linear system of equations as solving for a single vector valued quantity. Not only that, we want to move from our understanding in chapter 1 that a matrix was really just kind of a convenient tool. The augmented matrix was really a tool for us to keep track of the coefficients in our linear system without having the variables and the other notation crowding them out. So really, so far, a matrix has only been about bookkeeping for us. And we want to make it more sophisticated than that. We want to make a matrix something that's capable of acting upon a vector. Something capable of, in a real sense of algebra, multiplying a vector to transform that vector into something else. So that's the way that our understanding is going to evolve here. Linear algebra and the equations that define it are not about collections of variables, but they're about single entities called vectors. And matrices are not just a convenient way of keeping score, they're really the primary way in which vectors get moved around in linear algebra. So in this next couple of videos, we want to first focus on vectors for a while. And not only that, focus specifically on the one operation that makes vectors vectors. And that operation is called linear combination. So what we're going to do first is think about how linear combination of vectors relates to linear systems of equations that we already know quite a bit about. And then after that, we want to talk about the way in which every single linear system of equations, once we understand that its unknown is really a vector and not just a collection of quantities, that we can define that linear system of equations using multiplication by a matrix. And so really, every linear system of equations, and therefore every question that we can ask and answer in linear algebra pretty much, is related to a matrix vector equation, AX equals B. In a real sense, everything that we do this semester is about solving this equation. A times x equals b, where A is a matrix, x is an unknown vector, and b is a known vector. And we're going to think of the role of a matrix as transforming x into b. And our job is then to figure out how to solve that equation for x. So that's our roadmap for this chapter. We want to figure out what vectors are, how they work, what makes them tick, and then how matrices transform one vector into another in ways that will hopefully help us understand how to untransform and therefore solve the equation ax equals b to discover the unknown vector x. So let's get started.